Tonight, we're going to take a journey to a place that should not exist. A world wrapped in ice thicker than mountains are tall. A world where the sun is a distant pinprick, where temperatures on the surface plunge to 260 degrees below zero, where radiation so intense pours down from above that it would kill an unprotected human in 20 minutes. A world that, by every reasonable expectation, should be a frozen tomb. And yet, beneath that brutal, sterile crust, hidden from our eyes for billions of years, there is an ocean. Not a small pocket of water, not a frozen lake. A genuine, sloshing, liquid ocean. An ocean that contains more water than every sea, every river, every lake on Earth combined. Twice as much. Maybe 3 times as much. A black, silent, lightless sea, sealed under a vault of ice, churning quietly in the dark for longer than complex life has existed on our planet. Its name is Europa. It is the 4th largest moon of Jupiter, smaller than our own moon, easy to miss in a telescope, easy to dismiss as just another frozen rock orbiting a gas giant. But Europa is hiding something. Something that has scientists at NASA, at the European Space Agency, at universities around the world, more excited and more nervous than almost any other object in our solar system. Because if life exists anywhere beyond Earth, if there is a second Genesis, a second chance for biology to take hold in this dark corner of the cosmos, the smart money is on Europa. And by the end of tonight, you're going to understand exactly why this hidden ocean, this place we are racing to reach, might be the single most terrifying destination humanity has ever set its sights on. Before we go any further, if you find yourself drawn to these dark corners of the universe, to the mysteries that don't have neat answers, to the places where science starts to feel like something stranger, take a moment to like the video and subscribe. It costs you nothing, and it helps this channel keep diving into the cosmos with you. Now, let's begin. Picture yourself standing on the surface of Europa for a moment. The first thing you would notice is the silence. There is no atmosphere worth speaking of, no air to carry sound, no wind, no weather as we understand the word. Just stillness. Above you, Jupiter dominates the sky, a swirling, banded behemoth so enormous it occupies an area more than 24 times wider than our full moon does from Earth. Its great red spot, a storm large enough to swallow our entire planet, would rotate slowly across that hanging giant. Faint auroras might flicker at the moon's poles, painted by Jupiter's monstrous magnetic field. The ground beneath your boots would be ice harder than steel, stained in places with rust-colored streaks no one can fully explain. Long, dark cracks crisscross the surface in patterns that look almost deliberate, almost designed, as though something had drawn them with a finger across the entire moon. And beneath your feet, somewhere down there, miles below the crust, that ocean waits. Quiet, patient, possibly alive. Europa was first spotted by Galileo Galilei in January of 1610, when he pointed his crude homemade telescope toward Jupiter and saw 4 tiny points of light dancing around the giant planet. For 400 years after that, Europa was just a dot, a name in a catalogue, a curiosity. Nobody seriously imagined that a moon so small, so cold, so distant from the warmth of the sun could be anything other than a dead chunk of ice. Then in the late 1970s, the Voyager spacecraft swung past Jupiter on its way to the outer solar system, and the images it sent back rewrote everything we thought we knew. Europa was not a battered, cratered husk like our own moon. Its surface was eerily smooth, almost featureless in places, scored by enormous fractures that ran for thousands of miles. Something was resurfacing this world. Something was erasing the craters that should have accumulated over billions of years of bombardment, and whatever was doing it had to be coming from below. That was the moment, more than 4 decades ago, when serious scientists began to whisper the unthinkable. There might be an ocean down there, a real one. And if there is an ocean, then there might be heat, and if there is heat and water and the right chemistry, then there might be something else, something stirring. Something we are not prepared to meet. In the years since, the evidence has only piled up. The Galileo spacecraft, named for the man who first saw this little world, orbited Jupiter through the late 1990s and into the 2000s and made measurement after measurement that confirmed what scientists had only dared to hope. Europa's magnetic signature suggests a salty conducting layer beneath the ice. Plumes of water vapor have been observed erupting from its surface, geysers 200 kilometers high spitting out evidence of the ocean below. The chaotic terrain, the rafts of broken ice, the warm spots, the chemistry of the surface, every piece of the puzzle points the same direction. There is an ocean down there. It is enormous. It has been there for a very, very long time, and nobody knows what is in it. This is the promise of tonight's video. We are going to descend, layer by layer, into one of the most haunting environments in the solar system. We will look at how this hidden world was first discovered, what conventional science said was impossible about it, and the strange moment when the first cracks appeared in that certainty. We will examine the technology, the missions, the audacious spacecraft we are sending right now to peer beneath that icy shell. We will walk through the discoveries one by one, each stranger than the last, building toward a revelation so unsettling that it has changed how researchers talk about Europa behind closed doors. We will confront what this ocean might mean for our place in the universe, for the search for life, for the future of human exploration, and for the deeply uncomfortable question of what happens when we finally break through that ice. Because make no mistake, we are going. The Europa Clipper is already on its way, launched in October of 2024 on a journey of nearly 2 billion miles. Future missions are being designed right now to drill, to land, to send submarines into water that no human eye has ever seen. We are reaching out, deliberately, toward the dark beneath the ice. And what we find there may not just rewrite biology. It may force us to confront fears we have buried as deep as Europa buries its ocean. Stay with me. This descent is just beginning. To understand why Europa is so terrifying, you first have to understand how long this world hid from us. How many generations of human beings looked up at the sky without the slightest suspicion that one of the most extraordinary places in the solar system was sitting right there, in plain sight, masquerading as nothing more than a fleck of light beside a brighter planet. For most of human history, Jupiter itself was just a wandering star, brighter than most, traveling along the ecliptic in a way that the ancients found mysterious enough to name after their king of gods. The Babylonians watched it. The Egyptians watched it. The Greeks tracked its slow path through the constellations, but not a single one of them ever guessed that something was orbiting it. The idea that worlds could orbit other worlds was simply outside the bounds of what humans were allowed to imagine. That all changed on a cold January night in 1610, when a stubborn, argumentative Italian mathematician named Galileo Galilei pointed a homemade telescope, barely more powerful than a modern pair of binoculars, toward the bright dot of Jupiter. What he saw made no sense at first. 3 small stars in a perfect line beside the planet. He sketched them in his notebook. Then he came back the next night, and the stars had moved. By the night after that, there were 4 of them. And slowly, with the patience of someone who already knew his discovery would get him into trouble, Galileo realized that these were not stars at all. They were moons, tiny worlds circling Jupiter just as our moon circles Earth. The implication was earth-shattering. If things could orbit Jupiter, then the cherished idea that everything in the universe revolved around our own planet was a lie. Galileo had not just discovered 4 moons. He had discovered that we were not the center of anything. Those 4 points of light came to be known as the Galilean moons: Io, Europa, Ganymede, and Callisto. The names were not Galileo's idea. He wanted to name them after his patrons, the Medici family, but the wider scientific community eventually settled on names drawn from Greek mythology, picked out by the German astronomer Simon Marius. Europa was named for a Phoenician princess, a young woman from the old stories who was abducted by Zeus, the Greek version of Jupiter, when he disguised himself as a beautiful white bull. Zeus carried her across the sea to the island of Crete. And so, fittingly, this small icy world ended up named after a captive of the god whose planet it now orbited. There is something poetic about that name, this small, silent moon, this hostage of a giant, this place where something might still be waiting in the dark. For more than 300 years after Galileo, that is essentially all anyone knew about Europa. It was a dot, a reliable, well-behaved dot. Astronomers tracked its orbit, refined the math, learned that it circled Jupiter once every 3.5 days at a distance of around 670,000 kilometers. They calculated its diameter, somewhere around 3,100 kilometers, slightly smaller than Earth's moon. They estimated its mass and worked out that it must be made mostly of rock, with something lighter on the outside, something that reflected sunlight remarkably well. Brighter, in fact, than almost any other large body in the solar system. Europa shone like a tiny, polished pearl beside the muddy, striped Jupiter. But why it was so bright, what that bright surface was actually made of, those were questions no one could answer with the technology available. The first real clue came in the early 20th century, when astronomers began using spectroscopy to analyze the light reflected from distant worlds. Every substance has a kind of fingerprint, a pattern of specific colors it absorbs and reflects when light passes through or bounces off of it. By splitting the light from Europa into its component wavelengths and looking at which colors were missing, scientists could begin to deduce what was painted across its surface. The answer was water, frozen water. The brightness of Europa was not metal or unusual minerals, it was ice. An entire moon coated in ice, reflecting the distant sun back into space like a mirror. That alone was a remarkable discovery, but at the time, nobody made much of it. So what if there was ice? Mars had ice. Comets had ice. Ice was just a frozen, sterile, lifeless substance. Europa was assumed to be a frozen ball of rock, top to bottom, dead as any of the other airless bodies drifting in the outer solar system. Then came the space age, and everything began to shift. In December of 1973, the small Pioneer 10 spacecraft, the first object ever built by humans to reach the outer planets, swept past Jupiter and snapped a handful of grainy, low-resolution images of the Galilean moons. A year later, Pioneer 11 followed. The pictures were crude. Europa was still little more than a fuzzy disk, but for the first time, we were seeing it as a place, not just a point. A real spherical world with hints of features on its surface. Scientists studying those early images noticed something curious. Europa looked oddly smooth. There were no obvious mountain ranges, no huge crater chains. It looked too clean, like a cue ball that someone had just polished. But the pioneers were just the scouts. The real reconnaissance was still to come. In 1979, first Voyager 1 and then Voyager 2 flew past Jupiter, and the pictures they sent back arrived on Earth like a series of slow detonations. Suddenly, Europa was real. You could see it. You could see its surface in detail, and that surface was unlike anything anyone had ever seen before. There were almost no impact craters. The whole moon should have been pockmarked from billions of years of bombardment by asteroids and comets, just like our own moon, just like Mercury, just like Callisto, its sibling moon further out. But Europa was smooth, almost glassy, crisscrossed instead by enormous dark cracks, long lines that ran for thousands of kilometers, curving and crossing and overlapping in patterns that looked, to some scientists who saw them, eerily like the cracks in sea ice over a frozen lake. The kind of cracks that form when something underneath shifts and flexes. That observation, that one quiet observation, was the spark. A few researchers began to wonder aloud whether the smoothness and the cracks meant something impossible. Whether they meant that under Europa's icy skin, something was moving, something fluid, something warm enough to keep itself from freezing solid, even out here, more than 770 million kilometers from the sun. The whispers began in the late 70s and early 80s. A hidden ocean, a liquid sea, locked under the ice, sloshing in the dark. Most of the scientific community shrugged it off at first. The idea sounded absurd. There was no source of heat, no atmosphere, no sunlight. The conventional wisdom was clear. Europa was frozen through. Europa was dead. But conventional wisdom, as we are about to see, was about to suffer one of the most spectacular collapses in modern planetary science. To appreciate the magnitude of what was about to be overturned, you have to step inside the mindset of a planetary scientist in the late 1970s and early 80s. The textbooks of that era were full of confident statements about the outer solar system. They were not tentative. They were not full of asterisks. They were declarations, the kind of thing professors wrote on chalkboards and expected their students to memorize. And every single one of those declarations would, within a generation, be quietly torn up and thrown in the bin. The first piece of conventional wisdom was the most fundamental. Liquid water cannot exist in the outer solar system, period. The reasoning was clean and elegant. Water requires temperature. Temperature requires heat. Heat, in any meaningful planetary sense, comes from the sun. The sun, that nuclear furnace at the center of everything, radiates outward in all directions, and the amount of sunlight a body receives drops off with the square of its distance from the sun. Earth, sitting at 150 million kilometers from the sun, receives a comfortable 1,360 watts per square meter at the top of its atmosphere. That is enough to warm oceans, drive weather, sustain photosynthesis, keep an entire biosphere running. But Jupiter, where Europa orbits, sits at an average distance of 778 million kilometers from the sun. Out there, the same square meter receives roughly 50 watts. That is less than 4% of what Earth receives. Imagine standing outside on a summer afternoon and having 96% of the sunlight suddenly removed. That is Europa's normal. And it gets worse, because Europa's surface temperature, measured by every reliable method, hovered around -170 degrees Celsius. That is colder than dry ice. That is cold enough to make rock brittle and shatter like glass. In an environment that cold, the textbook said, water has only one possible state, and that state is ice. Solid, stable, forever. The second piece of conventional wisdom was about small worlds and heat loss. Planets and moons all start out hot. The energy of their formation, the kinetic violence of countless collisions during the early solar system, the heat from radioactive elements decaying inside their cores, all of it leaves these young bodies molten and glowing. But once a body forms, it begins to lose that heat to space. Heat radiates outward slowly, relentlessly, year after year, eon after eon. The smaller a body is, the more surface area it has relative to its volume, and the faster it loses heat. Earth, with a diameter of nearly 13,000 kilometers, is still hot inside. Its core is molten, its mantle convex. There is enough leftover heat, supplemented by ongoing radioactive decay, to keep our planet geologically alive, to drive plate tectonics, volcanism, mountain building. But Europa, with a diameter of just over 3,000 kilometers, was supposed to have cooled off long, long ago. The math was straightforward. A body that small, that far from the sun, with no replenishing heat source, should be frozen solid all the way through. From the cracked surface to the rocky core, Europa was assumed to be a dead lump of ice and stone, no warmer at its center than at its skin, geologically inert, tectonically silent, a fossil from the formation of the solar system, preserved in deep freeze. The third piece of conventional wisdom was about life itself. In the 70s and early 80s, the conditions believed to be necessary for life were a tight, restrictive list. You needed liquid water. You needed sunlight, because nearly every food web on Earth was understood at the time to depend ultimately on photosynthesis. You needed an atmosphere to protect organisms from radiation and to provide breathable gases. You needed a stable temperature within a narrow range. You needed all of these things at the same time, on the same world, for billions of years. The region around a star where these conditions could be met had a name. The habitable zone, sometimes called the Goldilocks zone. Not too hot, not too cold, just right. In our solar system, the habitable zone was understood to extend roughly from somewhere near Venus to somewhere near Mars. Earth sat comfortably in the middle. Beyond Mars, the habitable zone ended. There was no life out there. There could not be life out there. The asteroid belt was lifeless rubble. The gas giants were poisonous, crushing storms of hydrogen and helium with no surface to stand on. And the moons of those gas giants were frozen wastelands, beyond the reach of warmth, beyond the reach of biology. Europa, Ganymede, Callisto, the moons of Saturn, the moons of Uranus and Neptune, all of them were filed in the same category. Cold, dead, geologically and biologically inert. End of discussion. Even when the early Voyager images came back showing Europa's strangely smooth surface and its tangled web of cracks, the immediate response from the mainstream of planetary science was to look for explanations that did not require anything as wild as a liquid ocean. Maybe the surface was made of softer ice that flowed slowly under its own weight, smoothing out craters over millions of years like glacial flow on Earth. Maybe there were occasional bursts of cryovolcanism, slushy ice eruptions that would resurface small patches at a time. Maybe the cracks were the result of thermal contraction as the moon cooled, or stress patterns from Jupiter's gravity tugging on a solid ball. These were the respectable explanations. They were the explanations you could publish in a journal without raising eyebrows. The wild explanation, the idea of a global subsurface ocean of liquid water, was not officially forbidden, but it carried a stigma. It sounded like the kind of thing science fiction writers said when they wanted to set a novel somewhere exotic. It did not sound like the kind of thing serious planetary scientists were supposed to argue for in front of their colleagues. Behind this conservatism was a deep, almost philosophical commitment. The outer solar system had always been imagined as static, frozen in time, a kind of cosmic museum where the conditions of the early solar system were preserved untouched. Pluto was a frozen relic. The Kuiper belt was a frozen reservoir of leftover building blocks. The moons of the gas giants were frozen witnesses to a violent past, now silent. This was the picture, and it was a beautiful picture, and it was the picture that scientists had built their careers and their textbooks around. The idea that any of these bodies could be active, dynamic, geologically alive, harboring oceans, and possibly even biology, was not just contrary to evidence. It was contrary to a deeply embedded narrative about how the solar system was structured. Heat and life were inner system phenomena. Cold and stillness were outer system phenomena. That was simply the way things were. And then a small handful of scientists began looking at Europa's cracks again, and they began doing some math that nobody else wanted to do. And what they found did not just challenge the conventional wisdom. It did not just raise an awkward question. It detonated the entire framework. Because the math said that Europa should not be cold. The math said Europa should have a source of heat that was almost embarrassingly enormous. And the only way for that math to be wrong was if our understanding of how moons and planets worked was deeply, fundamentally broken. The first cracks in the old picture did not actually appear because of Europa. They appeared because of its volcanic neighbor. In the late 1970s, just months before Voyager 1 was scheduled to make its historic flyby of the Jovian system, 3 scientists at NASA Ames Research Center, Stan Peel, Patrick Casson, and Ray Reynolds, sat down with a problem that nobody else thought was particularly interesting. They were looking at Io, the innermost of the 4 big Galilean moons, and they were doing some careful math about its orbit. Io, like Europa, was supposed to be a cold, dead body. Same size category, same distance from the sun, same expected fate as a frozen relic. But Peel, Casson, and Reynolds noticed something nobody had taken seriously before. Io's orbit was not a clean circle. It was slightly stretched, slightly elliptical, and that ellipticity was being maintained by gravitational tugs from the other moons. As Io swung closer to Jupiter and then farther away on every orbit, the gas giant's enormous gravity squeezed and pulled at it. The whole moon, billions of tons of rock, was being kneaded like dough. The trio did the calculation. They asked how much energy that gravitational squeezing must be pumping into Io's interior, how much heat must be generated by all that flexing. The answer they got was enormous, so enormous that they almost did not believe it themselves. The math said that Io should be one of the most volcanically active bodies in the solar system. Not cold, not dead, hot, glowing, erupting. They wrote the paper, submitted it to the journal Science, and the paper was published in early March of 1979. 3 days later, Voyager 1 reached the Jovian system, and when its cameras turned toward Io, the images that came back made jaws drop in mission control. Io was covered in volcanoes, active ones. Plumes of sulfur dioxide were erupting hundreds of kilometers into space. Lava flows in shades of yellow, orange, and black sprawled across the surface. There were no impact craters at all on Io, because every square meter of it was being resurfaced constantly by molten material from below. The Peel, Casson, and Reynolds prediction had been completely vindicated within a week of publication. It is one of the most remarkable cases in the history of planetary science, a theoretical prediction confirmed almost immediately by direct observation. And it changed everything. Suddenly, the old assumption that small worlds far from the sun had to be cold and dead was not just questioned, it was demolished. There was a new mechanism on the table, tidal heating. the gravitational kneading of a body by a more massive partner. And if it could turn Io into a hellscape of volcanoes, then what was it doing to the other Galilean moons? What was it doing, specifically, to Europa? Europa is the next moon out from Io. It is locked in a gravitational dance with both Io and Ganymede, a mathematical waltz called an orbital resonance, in which the three moons keep tugging each other into elongated orbits that never settle down. Europa, like Io, is constantly being flexed by Jupiter's gravity. The flexing is less violent than what happens to Io, because Europa is farther from Jupiter, but it is still real, still continuous, still pumping energy into the moon's interior every single orbit. The calculations were redone, this time with Europa in the spotlight. The numbers that came out were not enough to make Europa volcanic, but they were more than enough to do something else. They were more than enough to keep a layer of water from freezing. The tidal heating budget was sufficient to maintain a liquid ocean beneath the ice, possibly hundreds of kilometers thick, possibly global, possibly the most enormous reservoir of liquid water anywhere in the solar system. The shift in the planetary science community was not instant. Old ideas die hard. Many researchers continue to insist that Europa was probably frozen solid, that any liquid water it might have once had was long gone, that the tidal heating estimates were exaggerated. But a new wave of younger scientists, looking at the Voyager images with fresh eyes, began to notice things that the conventional view could not explain. The dark cracks crisscrossing Europa's surface, called lineae, were not just simple fractures. They had structure. Many of them showed twin parallel ridges with a darker valley running between them. They looked, when you really studied them, like the fresh splits that open up in pack ice when warm water below pushes outward and breaks the surface. Some of the linear features curved in ways that matched the predicted stress patterns from tidal flexing, exactly the pattern you would expect if a thin shell of ice was being twisted over something fluid underneath. Then there was the absence problem. Europa's surface had almost no impact craters. The few that existed were small and oddly shaped, looking like they had been smeared or partially erased. The outer solar system is not a gentle place. Asteroids and comets have been raining down on everybody out there for over 4 billion years. A surface that old should be saturated with craters, like the moons Callisto and Ganymede. But Europa's crater count was so low that, when scientists calculated the implied surface age, the answer was somewhere between 40 and 90 million years. For context, the dinosaurs went extinct 66 million years ago. Europa's surface, in geological terms, is younger than the death of the dinosaurs. Something was scrubbing it clean. Something was constantly resurfacing this moon. And the only realistic mechanism anyone could come up with was an active interior, water or warm ice welling up from below, breaking through the brittle crust, refreezing in place, erasing the marks of ancient impacts. There were other oddities. Some regions of Europa, called chaos terrain, looked like someone had broken a frozen sheet into hundreds of jagged blocks and then frozen them back into place in random positions, as if rafts of ice had been floating on something liquid and then refrozen. Other regions showed strange domes and pits that resembled glacial features on Earth, places where water from below had pushed up against the underside of an ice shell. The dark reddish-brown stains running along many of the cracks looked organic, although nobody could yet say what they were. They might be salts, they might be sulfur compounds, they might be something else. Whatever they were, they had come from inside. By the late 1980s, the ocean hypothesis had moved from the fringes of planetary science to the center of a passionate debate. The textbooks had not yet been rewritten, but they were starting to feel out of date. A growing chorus of researchers was arguing that Europa was not what everyone had assumed, that underneath that frozen, fractured shell, something was hiding. The arguments were still mostly theoretical, still mostly based on indirect evidence and clever inference. What was needed was a closer look. A spacecraft, in orbit around Jupiter, taking its time, returning again and again to Europa, measuring it from every angle. Something more than a brief flyby. Something patient enough to settle the question once and for all. And as it happened, exactly such a mission was already being planned. To answer a question this big, about an ocean buried under miles of ice on a moon nearly 1 billion kilometers away, You cannot rely on theory and telescope images forever. At some point, you have to go there. You have to send something to Jupiter that does not just fly past in a hurry, but stays. Something that orbits, that returns to Europa again and again, that pokes and prods at the moon with instruments designed to sense things human eyes can never see. The mission that would finally do this was conceived in the late 1970s, approved in 1977, and christened with the only name that really fit: Galileo. The spacecraft, named after the man who had first seen these moons, would now be the one to finally understand them. Building Galileo was a nightmare of engineering, politics, and bad luck. The original plan was to launch it in 1982 on the Space Shuttle, paired with a powerful liquid-fueled upper stage that would hurl it directly toward Jupiter. That plan got changed, delayed, changed again. Then the Challenger disaster in January of 1986 grounded the entire shuttle fleet, and the liquid-fueled upper stage was deemed too dangerous to launch from inside a shuttle's cargo bay. Galileo had to be redesigned to use a weaker solid-fueled booster, and because that booster could not give the spacecraft enough velocity to reach Jupiter directly, mission planners came up with a creative solution. They would slingshot the spacecraft, using the gravity of Venus and Earth to bend its trajectory and add speed. Galileo would fly past Venus once and Earth twice, performing a strange interplanetary ballet before finally being flung outward toward Jupiter. The journey, which should have taken less than 3 years, would now take more than 6. Galileo finally launched in October of 1989 from the cargo bay of the Space Shuttle Atlantis. It then began the long and complicated dance through the inner solar system, gathering speed from each planetary encounter. As it traveled, the engineers tried to deploy the main high-gain antenna, the umbrella-shaped dish that was supposed to allow Galileo to send data home at high speed. The umbrella jammed. 3 of its ribs refused to lock open. Despite years of attempts, despite warming and cooling cycles, despite mechanical tricks, the antenna never fully deployed. Galileo would have to do its entire mission using a much smaller backup antenna, transmitting at only a tiny fraction of the originally planned data rate. It was a heartbreaking setback for a spacecraft that had taken decades to build. But the engineers and scientists at the Jet Propulsion Laboratory refused to give up. They rewrote the onboard software, found ways to compress images and data more efficiently, and turned a crippled mission into one of the most productive interplanetary missions ever flown. In December of 1995, after a journey of more than 6 years and 3.5 billion kilometers, Galileo finally entered orbit around Jupiter. It became the first spacecraft to orbit a gas giant, the first to spend years inside the Jovian system, the first to make repeated close passes of all 4 Galilean moons. And among its many targets, Europa was the one that consumed the imagination of the mission's scientists. Over the next 8 years, Galileo would make 11 close flybys of Europa, some of them skimming the moon at altitudes lower than commercial airlines fly over Earth. Each pass was an opportunity to gather a different kind of evidence, and the instruments on board were exquisitely chosen for the job. The solid-state imaging camera, the spacecraft's main eye, was a charge-coupled device, the same basic technology that powers modern digital cameras, but tuned and calibrated to extreme precision. It could resolve features on Europa as small as a few meters across in the closest flybys. The near-infrared mapping spectrometer broke incoming light into hundreds of separate wavelengths, allowing scientists to identify the chemical signatures of materials painted onto Europa's icy crust. They could tell the difference between pure water ice, salty ice, sulfur compounds, and various organic molecules. The plasma instrument measured the charged particles surrounding Europa, the constant rain of radiation pouring out of Jupiter's enormous magnetosphere. And the dust detector counted micrometeorite impacts, helping to characterize the environment the moon was traveling through. But the most important instrument on Galileo, the one that would crack the question of the ocean wide open, was something much less glamorous than a camera. It was a magnetometer, a sensor designed to measure magnetic fields. Most people, when they think of dramatic discoveries in space, picture beautiful images, glittering cosmic landscapes captured in full color. The truth is that a lot of the most important findings come from graphs and numbers and the patient measurement of invisible forces. The magnetometer on Galileo was a small set of sensors mounted on a long boom that stuck out from the spacecraft, far from the electronic noise of the main body. It could measure the strength and direction of magnetic fields with extraordinary precision, and it was about to deliver one of the most important pieces of evidence in the entire history of planetary exploration. The principle the magnetometer would exploit is something called electromagnetic induction. It is the same principle that powers electric generators on Earth. When a conducting material moves through a changing magnetic field, electric currents are induced in that material, and those currents in turn generate their own secondary magnetic field. Now consider Europa. It is orbiting deep inside Jupiter's gigantic magnetic field, one of the most powerful in the solar system. As Europa moves and as Jupiter rotates, that magnetic field is constantly shifting from Europa's point of view. If Europa contained a conducting layer, something like a salty ocean, then that ocean would have currents induced inside it, and those currents would generate a measurable secondary magnetic field. A frozen, dry, solid Europa would not produce such a signal. A Europa with a global salty ocean would. It was an elegant trap, and Europa was about to spring it. Galileo's mission planners scheduled flyby after flyby with the magnetometer running, sampling the magnetic environment at different positions and different times. The data came back compressed, slow, painstakingly transmitted through that crippled antenna over weeks and months. The scientists waited. The patterns began to emerge. Around the same time, on the imaging side, the high-resolution photographs of Europa's surface were arriving in fragments. The pictures showed details Voyager had only hinted at, the double ridges in stark relief, the jumbled blocks of the chaos terrain in unforgettable clarity, blocks the size of cities, frozen in place at angles that screamed of recent motion. There were strange dark spots, pits, domes, regions where the surface had clearly been disrupted by something rising from below. Each new image added more weight to a conclusion that the math, the theory, and the imagination of an earlier generation of scientists had pointed toward. But the magnetometer was the witness that could not be dismissed. The magnetometer was about to make the case airtight. The data was coming in. The instruments were ready. The question that had hovered over Europa for 2 decades was about to be answered. And the answer was not going to be the one the conventional wisdom had wanted. The first major discovery did not come in a single dramatic moment, the way Hollywood would have written it. It came the way real science usually comes, in trickles and confirmations and arguments at conferences, accumulating into something undeniable. The lead scientist for Galileo's magnetometer was Margaret Kivelson, a physicist at the University of California, Los Angeles. Kivelson and her team had been quietly gathering data through the late 1990s, comparing magnetic field measurements from one Europa flyby to the next, looking for the telltale signature that would mean a conducting layer underneath the ice. By 1998, the data was starting to tell a clear story. By the year 2000, Kivelson and her colleagues were ready to make the case publicly. They published their results in the journal Nature. And the conclusion was as direct as any planetary science paper has ever been. Europa had a conducting layer beneath its surface. The induced magnetic field signature was unmistakable. As Jupiter's enormous magnetic field swept past Europa, the Moon was responding the way a salty ocean would respond, generating its own secondary field in exactly the way physics predicted. The signature changed with Jupiter's rotation, just as it should. The strength of the response matched the expected response of a global subsurface ocean. There was no other reasonable explanation. Not a frozen interior, not a small lake or pocket of slush. Something planet-wide, something liquid, something salty enough to conduct electricity. The ocean was real. The reaction inside the planetary science community was a strange mix of vindication and quiet awe. For the scientists who had spent 2 decades arguing that Europa was probably hiding something, this was the moment their long fight paid off. For the holdouts who had insisted on a frozen interior, this was the moment the argument ended. There was no more room to dismiss the ocean as speculation. The magnetometer data, taken together with the imaging, the spectroscopy, the surface geology, the tidal heating models, all of it now fit one coherent picture. Europa had a global ocean of liquid salty water under its ice. The implications began to settle on the community like a slowly falling snow. This was not just a curiosity. This was a complete rewriting of where life might exist in the universe. The numbers being thrown around in the months and years that followed were almost too large to absorb. The ocean was estimated to be somewhere between 100 and 150 kilometers deep. For perspective, the deepest point in Earth's oceans, the Challenger Deep in the Mariana Trench, is just under 11 kilometers down. Europa's ocean might be more than 10 times deeper than the deepest place on Earth, and it covered the entire moon. There were no continents to interrupt it, no landmasses to push the water aside. Wrap a global sea around a small world, and the volume becomes astonishing. The best estimates put Europa's total ocean volume at somewhere around 2 to 3 times the total liquid water on Earth. A moon smaller than ours, holding more ocean than our entire planet. A buried sea so vast that, if you somehow drained Earth's oceans into Europa, there would still be room for more. The press coverage that followed was the first time a lot of the general public had ever heard of Europa as anything other than a mythological footnote. Articles appeared in major newspapers with headlines that bordered on the breathless. There was, briefly, even a moment when the public conversation about Europa overlapped with the public conversation about Mars. Mars had always been the default destination for the question of extraterrestrial life. Mars was nearby. Mars had once been warmer and wetter. Mars had captured the imagination since the late 19th century with its canals and its red glow. But Europa, in those early years after the magnetometer results, started to muscle into that conversation, because the question on Mars had always been whether life had ever existed there in the deep past, when the planet was younger and more hospitable. The question on Europa was different. The question on Europa was whether life might exist there right now, today, in this moment, in a dark sea that no eye had ever seen. Scientists who studied life on Earth began paying attention. Astrobiology, a young field at the time, suddenly had a target as compelling as Mars and arguably more so. The discovery of hydrothermal vents on the floor of Earth's oceans in the late 1970s and through the 80s had already changed what biologists thought possible. At the bottom of our oceans, in places where superheated water laden with minerals erupts from cracks in the seafloor, entire ecosystems thrive in absolute darkness, completely independent of sunlight. The tube worms, the clams, the strange shrimp that swarm around these vents do not photosynthesize. They depend on bacteria that perform chemosynthesis, drawing energy from chemical reactions between hot, mineral-rich vent fluids and cold seawater. These ecosystems are dense, diverse, and very much alive, and they were our first proof that life does not need the sun. Life only needs energy, in some form, and water, and the right chemistry. If Europa had a rocky seafloor under its ocean, and the magnetometer results combined with density measurements strongly suggested that it did, then that seafloor was almost certainly being warmed by the same tidal flexing that kept the ocean liquid. There should be heat there. There should be friction, geological activity, possibly even hydrothermal vents. And if there were vents, then there was an energy source. And if there was an energy source, and water, and the right chemicals leaching from the rock, then the prerequisites for life that we knew about on Earth were all present on Europa. The chain of reasoning was simple, and once you saw it, you could not unsee it. Europa had become, almost overnight, perhaps the most promising place in the entire solar system to search for living organisms that were not native to Earth. In the months and years following the announcement, textbooks began to be rewritten. The chapters on the outer solar system, the chapters that had described Europa as a frozen world, were quietly updated. The habitable zone, that comfortable concept that had defined where life could exist around a star, was no longer trusted as the final word. There could be habitable zones inside moons, deep below their surfaces, sustained not by sunlight, but by gravity. Astrobiologists started to call this concept the subsurface habitable zone, and once they did, They began looking around the solar system for other candidates. Ganymede, possibly. Callisto, maybe. Enceladus, a small moon of Saturn that was already showing some intriguing hints. Titan, with its hydrocarbon seas. Even Pluto and other dwarf worlds far beyond Neptune were now suspect. The solar system had been opened up. Europa had been the key that turned the lock. But the magnetometer had only told us one thing. There is an ocean. It was the answer to the first question. What it did not tell us was what was in that ocean, what was happening on its floor, what chemistry was unfolding in the dark. And as Galileo's other instruments continued returning data, as new images and spectra were studied in detail, the next layer of the story was about to emerge. And that layer was even stranger than the first. The second discovery began with light. Specifically, with the way light bounced off Europa's surface and split into a fingerprint of colors. While the magnetometer team was busy proving that the ocean existed, another group of scientists working with Galileo's near-infrared mapping spectrometer was busy asking a different question. What, exactly, was painted on Europa's icy crust? Pure water ice has a very clean spectroscopic signature. When sunlight bounces off it, the pattern of wavelengths that come back is well known and predictable. But Europa's surface, when carefully studied, did not look like pure water ice. The signature was messier. Mixed in with the ice were other things, hydrated minerals, compounds that contained water molecules locked into their crystal structures, materials that did not belong there if Europa was just a dead, frozen shell. The leading interpretation, after years of analysis by researchers including Thomas McCord and Robert Carlson, was that those reddish-brown stains running along the cracks and chaos regions were salts. Specifically, hydrated salts of magnesium and sodium, the same kind of compounds you would expect to find dried out from an evaporating sea. There were signatures consistent with magnesium sulfates, the same family of compounds that includes Epsom salt. There were signatures consistent with sodium chloride, ordinary table salt, although the form of it on Europa appeared to be modified by radiation. The implication was huge. If salts were sitting on Europa's surface, concentrated along the cracks and the chaos terrain, then those salts had almost certainly come up from below. They had been dissolved in the ocean, carried to the surface by liquid water or warm slushy ice pushing through the cracks, and left behind when the water flashed to frost in the vacuum and the cold. This was not just an ocean anymore. This was a chemically rich ocean, an ocean that had been in contact with rock, leaching minerals from the seafloor, dissolving them into solution, churning them up to the surface, and depositing their fingerprints in stains that could be mapped from space. The composition of those stains was a kind of grocery list of what was happening down there in the dark. Magnesium, sulfur, sodium, chlorine, all of these are elements that biology on Earth uses constantly. They are not exotic. They are not unusual. They are the building blocks of seawater. And here they were, painted across the face of a moon nearly 600 million kilometers from Earth, evidence of a sea that was not just liquid, but actively interacting with a rocky bottom. Then came another piece of the chemical puzzle, and this one was almost the opposite of the first. Europa's surface, it turned out, was being constantly bombarded by radiation from Jupiter's monstrous magnetosphere. Charged particles, mostly electrons and ions, slammed into the ice at energies that would kill any unprotected human almost instantly. That radiation was doing something to the ice. It was breaking water molecules apart. When a high-energy particle hits a water molecule, that molecule can fracture into hydrogen and oxygen. The hydrogen, being light, can escape to space. The oxygen tends to stay behind, combining with itself or with other molecules to form things like molecular oxygen and hydrogen peroxide. Spacecraft observations, both from Galileo and from Earth-based telescopes, started to detect these oxidants on Europa's surface. There was, quite literally, hydrogen peroxide painted across the ice. There was molecular oxygen trapped in the surface layers. The radiation was turning the top of Europa into a chemistry set, and one of the main products was oxidizing compounds. Now combine these two pieces of evidence and stand back and look at what you have. On the surface, radiation is constantly producing oxidants. In the deep, The ocean is in contact with a warm, mineral-rich seafloor, almost certainly producing reductants. Things like hydrogen and hydrogen sulfide and methane that come from chemical reactions between hot rock and water. On Earth, this combination is what life eats. Life on Earth fundamentally lives off of chemical gradients. It exploits the disequilibrium between reduced compounds on one side and oxidized compounds on the other. That gradient is the battery. That gradient is what every living cell on this planet, from the deepest hydrothermal vent microbe to the bird on your windowsill, is ultimately drawing power from. And Europa, against every prediction the old textbooks had ever made, appeared to have both halves of that battery: reductants from the seafloor below, oxidants from the irradiated ice above. The only question was whether the two halves could ever meet. That is when the ice shell itself started to get scrutinized with a new kind of intensity. If the ocean stayed sealed forever under a thick, immobile crust of ice, then the chemistry from the surface and the chemistry from the bottom would never mix. The battery would have two terminals, but they would never connect, and no current would flow. No life could exploit such a sealed system. But Europa's surface, as the years of analysis revealed, did not behave like a sealed system at all. The very salts that had been detected required that material from the ocean had reached the top recently, on geological timescales. The young surface, with its scarcity of craters, demanded that fresh material was constantly being brought up and recycled. The chaos terrain, those jumbled blocks that looked like refrozen icebergs, hinted that whole regions of the shell were periodically melting through and refreezing. There was exchange. There had to be exchange. The oxidants from the top must, at least sometimes, be reaching the ocean below. The reductants from the seafloor must, at least sometimes, be touching the underside of the ice. The community had not yet built the case all the way to the floor, but the shape of the building was now visible. Europa was no longer a frozen mystery. It was a living chemical machine. A world where water, heat, minerals, energy gradients, and a slow but persistent exchange between dark depths and bright surface all came together in exactly the recipe astrobiologists looked for when they tried to imagine where life could begin. The realization was profound enough that it began to seep out of the planetary science community and into the wider scientific world. Microbiologists started asking whether their model organisms, the bacteria that thrive in cold, salty water, in deep sea vents, in the brines beneath Antarctic ice, might have analogues out there. Geochemists started building simulations of what the chemistry of Europa's seafloor might look like. The picture became less of a wild speculation and more of a serious hypothesis with predictions that could be tested. And as the first discovery had been the ocean, and the second had been its chemistry, scientists now began to ask the obvious next question. If the ice was thinner in some places than in others, if there were regions where the ocean and the surface were almost touching, then perhaps the most important target on Europa was not the moon as a whole, but those specific places. Find the thin spots, map them, understand what was happening at those windows in the ice. Because something was about to be discovered there, something that would change the conversation again. And it was not going to be a quiet revelation either. It was going to come bursting up out of the ice, hundreds of kilometers high, in a way that nobody, even the most optimistic Europa enthusiasts, had quite predicted. In December of 2012, a German planetary scientist named Lawrence Roth and his team were doing something that sounds unglamorous, but turned out to be revolutionary. They were carefully studying ultraviolet images of Europa taken by the Hubble Space Telescope, looking for faint glows of hydrogen and oxygen near the moon's poles. These kinds of glows can be produced when charged particles from Jupiter's magnetic environment strike water vapor and cause it to fluoresce, lighting up like the gas in a neon sign. If you found such a glow, you could not be looking at solid ice. You could only be looking at water in the form of vapor, suspended above the surface, drifting outward into space. And on a frigid moon, where the surface temperature kept everything frozen, the only way to get water vapor was if something was actively venting from below. When Roth and his team finished their analysis, the image showed a faint, glowing arc near Europa's south polar region. The shape was consistent with a plume of water vapor rising hundreds of kilometers off the moon's surface, falling back down under its weak gravity, and then dissipating into space. The implications were almost impossible to overstate. Europa was not just a moon with an ocean. Europa was a moon that was, at least occasionally, spitting that ocean into space. The barrier between the buried sea and the outside universe was not absolute. There were leaks. There were geysers. There were brief, violent moments when the water from below punched all the way through the ice shell and burst upward in fountains that would dwarf anything on Earth. For context, the tallest geyser ever recorded on our planet was the Waymangoo Geyser in New Zealand, which back in the early 1900s occasionally shot water up to 460 meters. That is less than half a kilometer. Old Faithful, the famous geyser in Yellowstone, tops out at around 55 meters. The plumes detected on Europa were rising approximately 200 kilometers off the surface. 200 kilometers. Higher than the orbit of the International Space Station. From an icy moon smaller than ours, the numbers were staggering. The behavior was alien, and the consequence for science was enormous because it meant that you did not necessarily have to drill through miles of ice to find out what was in the ocean. You could fly a spacecraft through one of those plumes and sample it directly. The ocean was, sometimes, coming to us. The 2012 detection was tentative, and it had to be confirmed. The plumes were not constant. Follow-up observations sometimes saw them, sometimes they did not. They appeared to be intermittent, possibly tied to where Europa was in its orbit, possibly tied to the tidal stresses pulling at the ice shell. In 2014 and 2016, another team, led by William Sparks at the Space Telescope Science Institute in Baltimore, used Hubble in a different mode, watching Europa silhouetted against Jupiter and looking for dark patches against that bright background that would indicate plumes blocking light. Sparks and his colleagues found multiple candidate plume events in roughly the same regions Roth had identified. The case for plumes was getting stronger, although the community remained cautious. These were observations of objects very far away, and the signals were faint, and extraordinary claims required extraordinary evidence. The decisive moment came from a completely unexpected direction. In 2018, a researcher named Zhang Jia, working at the University of Michigan, had a thought that would have occurred to nobody who was not paying very close attention to old archives. Galileo had passed close to Europa back in December of 1997 on one of its 11 flybys. During that pass, the spacecraft had recorded unusual magnetic field disturbances and unusual plasma readings for which scientists at the time had no good explanation. They had filed it away as a strange anomaly. Jia and his collaborators went back and reanalyzed that data with 21 years of additional understanding, and the answer was immediate and stunning. Galileo had flown directly through a plume. The spacecraft had recorded the magnetic and plasma signatures of a column of water vapor erupting from the South Polar region. We had already done the impossible. We had sampled Europa's ocean. We just had not realized it. The reanalysis was crucial because it tied together everything. The Hubble observations of glow, the Hubble observations of silhouettes, the Galileo in situ measurements from 1997. They all pointed to the same conclusion. Europa was venting material from its interior into space, in spectacular plumes that rose higher than any geological feature on Earth. The plumes were intermittent, but they were real, and they were almost certainly fed by water from the ocean below. Whether the source was the ocean directly, or pockets of melt within the ice shell, or both, the connection between the buried sea and the outside world was no longer theoretical. It had been observed. This is where the pattern truly started to crystallize. Look at what we now had. A global subsurface ocean of liquid salty water, confirmed by magnetometer. A young, constantly resurfaced ice shell, revealed by the lack of craters. Hydrated salts on the surface, telling us the ocean was chemically active. Oxidants produced by radiation on the surface, providing one half of a biological energy gradient. A rocky seafloor likely producing reductants, providing the other half. Chaos terrain that suggested the ice shell was thinner in places, possibly allowing exchange between the surface and the ocean. And now, plumes of water vapor erupting from the South Polar region, opening direct windows between the hidden sea and the outside world. Every individual piece had been remarkable. Together, they amounted to something that the planetary science community could no longer treat as a wild possibility. Europa was not just possibly habitable. Europa was, by every reasonable measure, one of the most habitable environments anywhere outside Earth. The pattern was deeply unsettling in another way too, because it was familiar. Saturn's small icy moon Enceladus, studied by the Cassini spacecraft from 2004 to 2017, had been observed venting its own plumes from its south pole. Cassini had flown through those plumes repeatedly. It had detected water vapor, salts, ammonia, methane, hydrogen, and complex organic molecules, every one of which would be at home in a recipe for life. Enceladus, a moon so small you could fit it inside the British Isles with room to spare, was producing chemistry that astrobiologists found genuinely thrilling. And now Europa was joining that conversation. Two icy moons, in different parts of the solar system, both with subsurface oceans, both venting material into space, both potentially habitable. The solar system was no longer a place with one fluke biosphere on Earth and a bunch of dead rocks everywhere else. The solar system was starting to look like a place where habitable environments were common, where buried seas were everywhere, where the conditions for life might be the rule rather than the exception. And if that was true, then a question that had once seemed almost meaningless was becoming urgent and concrete. If habitable environments were everywhere, then where was the life? And what if it was right there, in Europa's ocean, waiting for us to come and find it? The implications were about to take a turn from the merely scientific to the genuinely disturbing. Because the next discoveries about Europa were going to suggest that what was happening in that ocean might be more active, more chemically rich, and far stranger than anyone had dared to predict. The fourth piece of the puzzle is where things start to get strange. Not strange in the sense of unfamiliar. Strange in the sense that the boundaries between the different parts of Europa, the boundaries we had drawn so cleanly in our minds, started to dissolve. We had been thinking of Europa as a system with three neat layers: a frozen, irradiated surface on top, a solid ice shell underneath that, a liquid salty ocean below the ice shell, sitting on a warm, rocky seafloor. 3 layers, 3 environments, a simple architecture. And then in 2011, a young planetary scientist named Brittany Schmidt published a paper that began to wreck that simple picture, and the wreckage has been spreading ever since. Schmidt and her collaborators have been studying the chaos terrain on Europa, those jumbled regions where the surface looks like someone took a frozen lake, shattered it into city-sized rafts of ice, slid the rafts around at random, and then froze them back into place. Conventional models had said this happened because warm material from the ocean was pushing up against the underside of the ice shell, melting through, allowing the surface to fracture and the blocks to drift. Schmidt's team did something different. They compared the patterns on Europa's chaos terrain to the patterns produced by ice shelves on Earth, specifically the way ice shelves over Antarctic subglacial volcanoes behaved. And they noticed something the ocean melt model could not explain. The geometry was wrong. The patterns of broken blocks did not match what you would expect from heat pushing up from a deep ocean far below. They matched, almost perfectly, the patterns you would expect from a body of liquid water located much higher up, sitting within the ice shell itself, just a few kilometers below the surface. The implication was startling. Embedded inside the ice shell, the same shell that everyone had thought of as a solid barrier sealing the ocean off from the world above, there appeared to be lakes. Pockets of liquid water trapped inside the ice. They were not the great ocean at the bottom. They were something new, halfway up. Schmidt's team estimated that some of these perched lakes might hold as much water as all of North America's Great Lakes combined. Not down at the bottom of Europa, where you would expect water to be. Hidden inside the ice itself, like droplets suspended in a glass of frozen wine. And if those lakes existed, then the ice shell of Europa was not a solid plug. It was a porous, dynamic, biologically interesting environment in its own right. It had its own little oceans, its own zones where water and ice coexisted, its own potential habitats. The number of places on Europa where life could potentially live had just multiplied. The strangeness deepened in 2022 when another researcher, Riley Kullberg, working with colleagues at Stanford, published a paper about Europa's double ridges. Those parallel pairs of icy hills running alongside many of Europa's cracks, hills that looked weirdly fresh and that nobody had ever fully explained, turned out to have an exact analogue on Earth. In Greenland, in places where ice sheets cover small pockets of water, similar double ridges are formed when those buried water pockets repeatedly freeze, expand, and squeeze the surrounding ice upward in symmetric pairs of ridges. Kullberg's team had used satellite radar to study a double ridge in Greenland in detail and then compared it, line by line, to the double ridges on Europa. The match was uncanny. The Europa ridges did not appear to be old, ancient features at all. They looked like the natural product of shallow water pockets near the surface, freezing and refreezing on cycles measured in mere thousands of years. The ice shell was alive with activity. Water was moving through it, pooling in it, pushing it up from below in ways that left signatures all over the moon. Now combine this with the oxygen problem. Throughout the 2000s, scientists had been estimating how much oxygen was produced on Europa's surface by radiation breaking apart water molecules. The numbers had been encouraging. Tens to hundreds of kilograms per second, depending on the assumptions, possibly more, all of it potentially feeding the ocean below and providing energy for life. Then in 2024, results from NASA's Juno spacecraft, which had performed a close flyby of Europa, were published. Juno measured the actual flux of oxygen being produced, and the number was much lower than expected, roughly 12 kilograms per second, about 1/10 of some earlier estimates. That was still enough, theoretically, to support some kind of biology, but it was far less than had been hoped, and it raised a deeper question. If less oxygen was being made than expected, was the surface-to-ocean chemical pipeline as efficient as people had assumed? Was the battery as strong as we had thought? Or was the whole picture more constrained, more delicate, more conditional than the optimistic models had suggested? Then came the carbon. In 2023, a team using the James Webb Space Telescope made another announcement. They had detected carbon dioxide on Europa's surface, concentrated in a particular region called Terra Regio. And by analyzing the form and distribution of that carbon dioxide, they had concluded that it almost certainly came from the ocean below, that this was not carbon delivered from comets or formed by radiation, but carbon that had originated inside Europa, in the buried sea, and had been brought to the surface by recent geological activity. Carbon, inside Europa's ocean. Carbon is the backbone element of every form of life we know. Carbon plus liquid water plus chemical energy is the basic recipe for biology as we understand it, and every single one of those ingredients was now confirmed to be present. But this is the part where the paradox really starts to bite. The ingredients are there, the water is there, the energy is there, the carbon is there, the salts are there, the dynamic ice shell is there, the plumes are there, the chemical gradients are there. Everything you would put on the wish list for an inhabitable world is checked off, and yet the actual chemistry seems oddly restrained. The oxygen flux is lower than hoped. The plumes are intermittent and difficult to observe. The exchange between surface and ocean might be much slower than we had imagined. The ice shell is thicker in many places than we wanted it to be, estimates now ranging from a few kilometers to perhaps 30 kilometers thick. Each new measurement seems to give and take at the same time, providing tantalizing evidence of habitability while also raising new questions about whether that habitability is fully realized. This is what makes Europa more disturbing than a simpler story would. If everything had simply pointed to a thriving alien sea, that would be wondrous, but it would not be unsettling. What is unsettling is that Europa keeps half answering its own questions. It is habitable but not obviously alive. It is dynamic but not predictably so. It is chemically rich, but with gaps in the data we cannot yet fill. The pattern that emerges is not a clear picture. It is the silhouette of something, a shape just out of focus, a moon that seems to be hiding the most important answer right behind the answers we already have, and it was about to deliver something even more unsettling. Something that would force the entire conversation, for the first time, into territory that nobody in planetary science had quite been prepared to enter. Here is the revelation that reframes everything else. Take a moment and try to absorb it, because once you do, Europa stops being a curiosity and becomes something genuinely staggering. Europa's ocean is old. Not old in the human sense. Not old in the geological sense we're used to. Old in a way that makes the entire history of life on Earth feel young by comparison. The best estimates we have, based on the tidal heating models, the orbital configuration of the Galilean moons, and the chemistry of Europa's interior, suggest that this hidden sea has existed in essentially continuous liquid form for somewhere between 3.5 and 4 billion years. That number alone is hard enough to digest, but the truly disturbing comparison is with our own planet. Earth's surface, the surface we know and live on, is constantly recycled. Plate tectonics carries old seafloor down into the mantle and creates fresh seafloor at mid-ocean ridges. The oldest actual seafloor on Earth, the oldest patch of crust at the bottom of the ocean that has not been swallowed and remade, is only about 200 million years old. The deepest, most ancient parts of the rock under our feet that have stayed put through geological history are scattered relics on continents, fragments of ancient cratons. Earth is, in a real sense, a planet that keeps wiping its own slate clean. Europa does not do that. Europa cannot do that. There are no plate tectonics in the same sense. There is no subduction zone swallowing its seafloor. The rocky bottom of Europa's ocean, the floor where any chemistry between rock and water is taking place, has been sitting there in contact with that same dark sea for possibly 4 billion years. Continuously, without interruption, without any reset event of the kind that periodically reshapes the floors of Earth's oceans. If anything started growing on that seafloor early in Europa's history, it has had as much time to evolve as life has had on Earth. Maybe more. Because while complex life on Earth only really took off in the last 600 million years, in the wake of the Cambrian explosion, life in Europa's ocean would have had the entire window. From the first liquid water that formed under its ice, all the way to right now, with no impact extinctions reshuffling the deck, no asteroid strikes wiping out dominant lineages, no ice ages, no nothing. Just dark, steady, billion-year evolution under conditions that have never significantly changed. Now think about what that means. We sometimes imagine, when we picture finding alien life, that we will find slime, microbes, mats of bacteria clinging to rocks, the simplest possible life forms, because life is fragile and getting started is hard, and most environments only barely permit anything alive at all. That mental image is comforting, in a way. It keeps the discovery manageable. It keeps the universe small enough to fit in our head. But Europa's ocean is not a marginal environment. If everything we have learned in the last few decades is correct, it is one of the most stable, energy-rich, water-rich, mineral-rich environments anywhere in the solar system, and it has been that way for nearly the entire age of Earth. If life ever got started in there, it has had time to do more than just survive. It has had time to elaborate, to diversify, to climb whatever evolutionary ladders are possible in a sunless, sealed, salty deep. What we might find down there, if we find anything, might not look like the simple microbes our intuition wants to predict. It might be something complex, something layered, something with its own ecology, its own food chains, its own structures, evolved entirely in isolation, with no reference point to anything on Earth. This is the part that makes researchers genuinely uneasy when they speak about Europa off the record. Because whatever lives down there, if anything does, has spent 4 billion years evolving in absolute darkness, under crushing pressure, in a chemistry that resembles nothing on Earth's surface, with no connection of any kind to our own tree of life. There will be no shared ancestry. None. The deepest microbe in a hot spring at the bottom of the Pacific is still a cousin of yours. You share genes with it. You share fundamental biochemistry, the same amino acids, the same nucleic acids, the same metabolic pathways inherited from a common ancestor that lived more than 3.5 billion years ago. Europa's biosphere, if it has one, would share nothing with you. It would be the result of a completely separate origin of life, what astrobiologists call a second genesis. It would be a parallel tree of life. a second branch of the cosmic experiment growing in the dark, where nobody on Earth has ever been able to look. And here is where the unease cuts deepest. We cannot know what such an organism would even look like at the molecular level. It might use carbon like us, because carbon is uniquely good at building complex molecules. But it might use different amino acids, different nucleic acids, different chirality, different solvents in its cells, different ways of storing energy. It might not be classifiable using any of the categories we have built for terrestrial biology. Picking up a piece of Europan life and putting it under a microscope would not be like looking at an alien plant. It would be like looking at a new kind of physics, and there is no guarantee, none whatsoever, that we could even recognize it as life when we saw it. Our detectors are calibrated to find Earth chemistry. Our assays are designed to find Earth biomolecules. Europa's life might be invisible to us, sitting right in our sample, until we somehow stumble onto the right way to look. Now apply the second twist. If Europa is this habitable, this old, this energetically rich, and we look down there and find nothing, no life at all, then we have to take seriously a much darker possibility. The leap from non-living chemistry to living chemistry, the so-called origin of life, might be vanishingly rare. So rare that even 4 billion years of perfect conditions in a global ocean does not guarantee it happens. If Europa is empty, then life on Earth becomes much more of a freak event. The galaxy starts to look much emptier. The great silence we observe in the cosmos starts to make a different kind of sense. Europa, in that scenario, would not just be a moon, it would be a test. A clean experiment running for 4 billion years on whether life can begin in a habitable environment. And if it failed, then we have to ask what that means about us. Either way, the answer is unsettling. If Europa is alive, we are about to make contact with a form of life utterly disconnected from anything humanity has ever known, evolved over a timescale that dwarfs human civilization to the point of farce. If Europa is dead, then our own existence becomes more terrifying, because it means that even the perfect recipe, given billions of years to try, may not be enough. There is no neutral outcome here. Europa, the small icy moon Galileo first spotted 4 centuries ago, has somehow become the place where one of the deepest questions humanity has ever asked is going to be answered, and we are about to go knock on its door. Step back from Europa for a moment and look at what its discovery has done to the rest of science. The ripples have spread out from this one moon in ways that have quietly rebuilt entire fields. A textbook from the 1970s and a textbook from today, side by side, would tell 2 completely different stories about where in the universe life can exist. And the line between those 2 stories runs right through Europa. Start with the concept that died first. The habitable zone, that Goldilocks band around a star where temperatures allow liquid water on a planetary surface, used to be the single most important idea in astrobiology. Find the habitable zone, find the planets inside it, and you have your candidates for life. Everything outside that zone was filed away as too hot or too cold, and the search did not really go there. Europa shattered that framework. Europa sits far outside the traditional habitable zone of our Sun, in a region where the textbook said liquid water was impossible, and Europa nonetheless has more liquid water than Earth does. The energy that keeps that water liquid does not come from sunlight at all. It comes from tides, from the constant gravitational squeezing of a moon by its host planet. That is an energy source completely unrelated to the traditional habitable zone. It does not care how far the sun is. It does not care about temperature gradients across an orbit. It is a different kind of furnace entirely, and Europa proved it could keep an ocean alive for billions of years. Once that idea was accepted, scientists started asking the obvious question: where else might this be happening? And the answer, embarrassingly, was almost everywhere. Astronomers and planetary scientists began going back through the catalogue of moons and dwarf worlds in our own solar system and rerunning the math. Saturn's moon Enceladus, as already mentioned, turned out to have its own subsurface ocean, complete with plumes and chemistry that astrobiologists found nearly as exciting as Europa's. Ganymede, the largest moon in the solar system, also a Galilean moon, also under Jupiter's gravitational influence, appears to have a deep ocean of its own, possibly sandwiched between layers of different forms of ice. Callisto, the outermost Galilean moon, may also harbor liquid water under its crust. Titan, Saturn's largest moon, almost certainly has a subsurface water ocean in addition to its weird hydrocarbon seas on the surface. Even Pluto, the small dwarf world out beyond Neptune, was found by the New Horizons spacecraft in 2015 to show evidence consistent with a subsurface liquid water ocean. Triton, Neptune's strange backwards orbiting moon, probably has one too. Mimas, a small moon of Saturn previously dismissed as a frozen ball, has recently shown evidence of a recently formed ocean beneath its ice. A category of object came out of all this that simply did not exist a generation ago. Planetary scientists now talk about ocean worlds as their own class of body in the solar system, distinct from rocky planets and gas giants and ice giants. There may be more ocean worlds in our solar system than there are rocky planets. We have exactly 4 rocky planets: Mercury, Venus, Earth, and Mars. We may have more than twice that number of ocean worlds, possibly far more. The implication is genuinely revolutionary. The default state of a moon at sufficient distance from its host planet, with sufficient tidal heating, with sufficient internal heat from radioactive decay, may not be frozen dead rock. The default state may be a hidden sea. Earth, with its surface ocean exposed to sunlight, may actually be the unusual case. The galaxy may be full of worlds whose oceans are quietly hidden under ice, where life, if it exists, lives in darkness rather than in sunshine. That single shift, from surface oceans being the norm to hidden oceans being the norm, has changed how exoplanet research is conducted as well. Astronomers searching for habitable planets around other stars used to focus exclusively on rocky planets in the traditional habitable zone of sun-like stars. Now they pay attention to icy moons that might orbit gas giants in other star systems. They pay attention to rogue planets, drifting alone in the dark between stars, which were once dismissed as utterly dead, but which could host subsurface oceans warmed entirely by their own internal heat. There are estimated to be billions of such rogue planets in our galaxy. If even a small fraction of them harbor liquid water oceans under ice, then the number of potentially habitable environments in the galaxy is not in the millions or billions. It is potentially in the hundreds of billions. Europa, by existing, has made the universe a much friendlier place for life, or at least a place with vastly more locations where life could begin. The Drake equation, that famous attempt to estimate the number of communicating civilizations in the galaxy, has been affected too. Several of its factors, the fraction of stars with planets, the number of planets per star that could support life, depended on assumptions about the traditional habitable zone. Those assumptions are now obsolete. Even pessimistic versions of the equation, when updated for the existence of ocean worlds, give numbers significantly higher than what previous calculations produced. We do not know if those numbers translate into actual civilizations, but the raw number of potentially habitable environments is now vastly larger than it was 30 years ago. The cosmic real estate market for life has expanded enormously. Inside biology itself, Europa has helped drive the explosion of interest in extremophils, the organisms on Earth that live at the edges of what we used to consider habitable. Microbes that thrive in nearly boiling acidic hot springs. Microbes that live inside Antarctic ice cores and inside rocks miles underground. Microbes that survive radiation doses that would kill almost anything else, like Deinococcus radiodurans, which can take 1,000 times the lethal dose for a human and walk away. The more we look at the strange corners of Earth's biosphere, the more we find life clinging on in conditions that look almost designed to mimic Europa or Enceladus. The boundary between Earth biology and possible Europa biology becomes less of a chasm and more of a continuum. Bacteria that breathe iron, microbes that use hydrogen and sulfur and methane to power themselves, organisms that live without sunlight, without oxygen, without any of the things we used to consider essential. All of them have helped us imagine what life on Europa might look like and how we might recognize it if we saw it. Even within geology, Europa has changed things. The realization that ice can flow like rock, that ice shells can convect, that water can move through ice in ways nobody had documented before, has spilled over into glaciology on Earth. Studies of Antarctic ice sheets, of Greenland's perched lakes, of subglacial environments under our own polar caps have been informed by what we are learning on Europa. The ice on a moon nearly 1 billion kilometers away is teaching us about the ice in our own backyard. The lessons run both ways. A field that used to be entirely Earth-focused now thinks routinely about icy worlds elsewhere, and that broadened perspective is producing better science on both ends. The Europa discovery did not just add a chapter to the textbooks, it rewrote large parts of them, and the rewriting is still going on. It is one thing for a scientific discovery to rearrange a textbook. It is another thing entirely for it to change how a species understands itself. And that is the quiet weight that Europa carries. Whatever happens next, whether we find life there or do not, the existence of a sealed ocean on a moon next door has already done something to how humanity sees its own place in the universe, and the implications of that shift are starting to ripple outward in ways most people have not yet felt. For most of human history, the question of life beyond Earth was an abstract question. It was the kind of thing you debated in dorm rooms and on late-night radio shows, the kind of thing that lived in science fiction novels and the imaginations of children. The reason it was abstract was simple. There was no place to actually look. We could squint at Mars through telescopes, draw imaginary canals onto its surface, dream of bug-eyed Venusians or moon men, but it was all fantasy. There was nothing concrete. There was nothing measurable. There was nothing we could go visit and find out. Europa changed that. Europa gave the question of extraterrestrial life a fixed address, a specific moon, a specific ocean, a specific volume of water, a specific timeline of evolution, a specific destination we can send a spacecraft to and ask the question directly. The abstraction has, for the first time in human history, become an experiment. That is a profound change in the kind of question humanity is asking. We are no longer asking, in the philosophical sense, whether life exists elsewhere. We are asking, in the operational sense, what happens when we look. And the act of being able to ask that operational question changes us. It changes parents talking to their children about what they want to do when they grow up. It changes classrooms, because suddenly biology is not a closed system anymore. Suddenly, the trees of life you draw in 8th grade may not be the only ones that exist. It changes the way the next generation of scientists chooses their careers. There are graduate students entering astrobiology programs right now whose entire professional lives will be shaped by what Europa contains. That kind of redirection of human attention is rare. It usually only happens when a discovery is enormous, but the personal stakes go further than career choices. Imagine, for a moment, what it would feel like to wake up to the news that life had been confirmed in Europa's ocean. Not as a possibility, not as a hypothesis. Confirmed. Real organisms recovered from a plume, analyzed in a clean room, photographed under microscopes, sequenced if possible, characterized in whatever way our science is up to. The first moment of certainty that we are not alone, not in the cold, dead universe sense, but in the small, intimate sense of having neighbors right next door. That moment would not be like the discovery of an exoplanet. Exoplanets are abstract too. They are pixels of light, statistical inferences about distant worlds that we will never visit in any human lifetime. A confirmed living organism from Europa would be something tangible, something held in human hands. Something we could study every day. Something we could place beside the bacteria on our own kitchen counters and compare. The strange intimacy of that, the closeness of life that is not us, would be unlike anything any human society has ever had to integrate. It would also force some uncomfortable conversations. Every major religion would have to grapple with the meaning of life on another world. Some would absorb the discovery easily, treating it as an expansion of God's creation. Others would face serious doctrinal questions. Philosophical schools, ethical frameworks, even legal systems would have to reckon with the existence of life that did not evolve from Earth, that may not be conscious in the human sense, but that nonetheless represents a separate origin event. Do we have responsibilities to such organisms? Do they have any kind of rights, by any meaningful definition? If we bring samples back to Earth for study, are we doing science, or are we doing something closer to abduction? These are not idle questions. There are already real debates inside the planetary science community about what protocols we should follow if we encounter Europan life. The principle of planetary protection, the doctrine that says we should not contaminate other worlds with Earth microbes and should not contaminate Earth with possible alien microbes, has been a quiet but serious thread in mission planning for decades. With Europa, it becomes urgent. The Europa Clipper, the spacecraft already on its way, was sterilized to within an inch of its life. Future landers and submarines will face even more demanding requirements. Because if we accidentally seed Europa's ocean with Earth bacteria, we may never know whether what we find there is native or imported. The science could be ruined before we even begin. And the contamination concern runs both ways. If we bring samples back to Earth, even small ones, even samples we believe to be sterile, we are introducing material from an entirely separate origin of life into the only biosphere we have. We do not know what such material would do. Most likely, alien microbes would be unable to function in Earth's chemistry, since their entire biology evolved for a different environment. Most likely, they would simply die. But most likely is not certainty. The history of biological invasions on Earth, where species cross from one continent to another and devastate ecosystems they had no business entering, is a cautionary tale. We have to think very carefully about whether the curiosity is worth the risk. The decisions about how to handle Europa samples will be among the most consequential biological decisions our civilization has ever made. There is also the more inward-facing question. What does it do to us as a species to know what is happening in Europa's ocean, regardless of what we find? If we find life, it tells us the universe is alive, that biology is not a freak accident, that we are part of a vastly larger story. That knowledge could be unifying. It could pull human attention upward, away from the petty disputes of our small planet, toward a cosmic scale of significance. It has happened before. The first photographs of Earth from space, especially the famous blue marble image taken by Apollo 17 in 1972, fundamentally changed how the public thought about our planet. They made it feel small, fragile, shared. A confirmed living world in our own solar system would have a similar effect, multiplied. Or it could fail to unify. It could be politicized, weaponized, turned into another front in old arguments. Humans have a way of fighting over the most expansive discoveries. There is no guarantee that Europan life would bring us together rather than be added to the list of things we argue about. And if Europa is empty, that emptiness will mean something too. It will mean that the universe is colder than we hoped, that life on Earth is more precious than we knew. That whatever we have here, fragile, irreplaceable, may be the only spark of its kind for trillions of kilometers in any direction. That kind of knowledge changes how you treat your own home. The personal stakes, in either outcome, are not small. They are about who we are. For all the discoveries we have piled up over the last few decades, the honest truth about Europa is that we still know almost nothing about it. The shape of the moon, the basics of its orbit, the rough structure of its interior, these we have figured out. But the actual contents of the ocean, the actual character of the seafloor, the actual presence or absence of any kind of biology, all of these remain open. We have been studying Europa in a serious way for less than 50 years. The Galileo mission ended in 2003 when the spacecraft was deliberately crashed into Jupiter to prevent any chance of it contaminating Europa with Earth microbes. Since then, we have squeezed every drop of insight from the data Galileo collected. We have used Hubble. We have used Juno. We have used the James Webb Space Telescope. We have squinted at Europa from across vast distances and inferred what we could. But to actually answer the questions that matter, we need to go back. And we need to bring better instruments. And in some cases, we need to go through the ice. The most ambitious answer to that need is already in flight. The Europa Clipper, the largest interplanetary spacecraft NASA has ever built for a planetary science mission, launched in October of 2024 aboard a SpaceX Falcon Heavy rocket from Kennedy Space Center. It is currently making its long journey to the Jovian system, a journey that will involve a gravity assist past Mars in 2025 and another past Earth in 2026. before finally arriving in Jupiter orbit in April of 2030. Clipper is not designed to orbit Europa directly, because the radiation environment around the Moon is so brutal that any spacecraft staying there continuously would be fried in months. Instead, Clipper will orbit Jupiter in a long looping path that brings it close to Europa repeatedly, almost 50 times over the course of its mission, each pass allowing it to gather data without lingering in the radiation belt long enough to die. The instrument's suite is staggering. There are cameras that will image the surface at resolutions far better than anything Galileo achieved, allowing geologists to map the chaos terrain, the double ridges, and the cracks in fine detail. There is an ice-penetrating radar designed to bounce signals through the ice shell and map its thickness directly, which would finally resolve the long-running question of how thick that shell actually is and whether it varies from place to place. There is a thermal imager looking for warm spots, places where heat from below is bleeding through to the surface, which might mark where ocean water is closest to breaking through. There is a powerful magnetometer, more sensitive than Galileo's, designed to refine our understanding of the ocean's depth and salinity. There is a mass spectrometer designed to taste any vapor or particles in Europa's thin exosphere, and if Clipper is lucky enough to fly through a plume, it will analyze that plume in real time. There are spectrometers covering wavelengths from ultraviolet to infrared, designed to map the surface chemistry in detail, looking for organic compounds, looking for fresh deposits, looking for anything that might be a chemical fingerprint of life. Clipper will not, by itself, prove or disprove the existence of life on Europa. That is not its design goal. Its job is to characterize the habitability of the Moon. To establish, with as much certainty as remote sensing allows, whether Europa really has the conditions necessary for life. To find the most promising places, the thin spots in the ice, the most active plume sources, the regions of fresh chemistry, so that a future mission can target them. Think of Clipper as a scout. It is the reconnaissance run before the real expedition. Alongside Clipper, the European Space Agency has its own mission already in transit. JUICE, the Jupiter Icy Moons Explorer, launched in April of 2023 and is on its way to the Jovian system, with arrival planned for July of 2031. JUICE is focused primarily on Ganymede, where it will eventually enter orbit, but it will also study Europa and Callisto along the way. Between JUICE and Clipper, the early 2030s will see the most intense scientific examination of Jupiter's icy moons in human history. Two spacecraft from two different space agencies, equipped with complementary instruments, working through the Jovian system at the same time. Most planetary scientists will tell you, off the record, that the 2030s will probably be remembered as the decade when our understanding of ocean worlds went from a sketch to a portrait. But even with both missions performing flawlessly, there will still be a fundamental limit to what we can learn. We cannot see through the ice with cameras. Radar can map its thickness, but cannot show us what is in the water below. We can sample plume material if we are lucky, and that will tell us something about ocean chemistry, but plumes are not constant and may not represent the deep ocean perfectly. There will come a point where we have squeezed all the science we can out of remote sensing, and we will have to make a hard decision. To find out what is really in Europa's ocean, we are going to have to touch it. That is where things get speculative. Mission concepts for actually landing on Europa and for eventually drilling or melting through its ice shell have been studied seriously for decades. The proposed Europa lander, a concept NASA has explored repeatedly, would set down on the surface, collect samples of fresh material, and analyze them in place with biosignature detectors far more sensitive than anything Clipper carries. Beyond the lander concept lies the cryobot, a probe designed to melt its way slowly down through the ice using a heated nose cone, trailing a fiber optic communications tether behind it. A cryobot that successfully reached the ocean would deploy a small submarine, an autonomous underwater vehicle that could explore the dark sea below. Designs for such submarines exist on paper. Prototypes are being tested in Antarctic lakes and under polar ice on Earth, in environments deliberately chosen to mimic what Europa might present. None of this technology is ready for prime time. Funding for the lander has been on and off again for years. The cryobot and submarine concepts are decades from being mission-ready, if they ever are. The radiation environment alone is a vicious obstacle. Electronics on Europa's surface would need shielding that adds enormous mass. Communications back to Earth across more than 500 million kilometers through ice that may be tens of kilometers thick would require breakthroughs we have not yet achieved. The honest timeline is sobering. Clipper data will not start arriving until 2030. Any follow-up mission concept, even if approved immediately after Clipper's findings, would take another decade to design, build, and launch. A lander on Europa in the 2040s is plausible. A successful subsurface mission, with a probe actually reaching the ocean and sampling it, is not realistic before the 2050s or 2060s at the earliest, and may not happen even then. The children alive today are the ones who will probably see the answer. Not us, watching today, but the generation we are raising. Europa's secrets will be revealed slowly, across decades, in patient and expensive steps. And we have to live with that pace, because the alternative, rushing in carelessly, could destroy the very thing we are trying to study. Stand for a moment with the full picture of Europa in your mind, and let yourself feel how strange our position actually is. There is a sea, larger than Earth's, hidden under ice on a moon orbiting a planet we can see with our naked eye on any clear night. That sea has been there, sloshing quietly in absolute darkness, for almost the entire age of our solar system. It was there when the first single-celled organisms on Earth were stirring in our own primitive oceans. It was there while dinosaurs walked our continents. It was there while the first humans painted on cave walls. It was there yesterday. It is there right now, as you read these words. And we have only known of its existence with any confidence for less than 30 years. Our entire species walked under that sky for hundreds of thousands of years, ignorant. Every philosopher, every priest, every astronomer who looked up before the late 20th century thought about meaning and origins and life in the universe without knowing that one of the largest bodies of liquid water in the solar system was a few 100 million kilometers above their heads. Plato did not know. Buddha did not know. Galileo, who saw Europa first, did not know. Newton did not know. Einstein did not know. The knowledge that there is a sea up there belongs to us, to this generation. The accident of when we were born has given us access to a piece of cosmic information that nobody alive 100 years ago had any way to suspect. That alone is staggering. We talk about our species as if it has had a steady relationship with the universe, as if each generation looks up at roughly the same sky. But that is not true. Each generation looks up at a different sky, because what we know about the sky is constantly being rewritten. The Europa we look at when we lift our eyes today, knowing what we know, is not the same Europa our grandparents looked at. They saw a small bright dot beside a giant planet. We see, when we look, an ocean, a buried sea, a potential second tree of life. That kind of generational shift in cosmic awareness is one of the rarest experiences a species can have. It probably will not repeat with the same intensity for centuries. We happen to be alive at the exact moment in human history when the hidden oceans of the solar system are coming into focus. The accident of timing is precious. It is also a little terrifying, because once you have looked, you cannot unlook. The universe we live in is now a universe of buried seas, of hidden possibilities, of moons that may be alive. And that knowledge sits on us whether we want it to or not. Now consider, in the same quiet way, the scale problem. Europa is one moon, around one planet, in one star system. Our solar system is one of an estimated 400 billion star systems in the Milky Way. The Milky Way is one of an estimated 2 trillion galaxies in the observable universe. If buried oceans are common, as the discoveries in our own neighborhood now strongly suggest, then the number of habitable environments in the universe is not a number that human minds were ever evolved to comprehend. It runs into the trillions of trillions. Most of those environments will never be visited by anyone from Earth. They will exist, they will persist, they will possibly contain life, and they will be forever beyond our reach. Europa, by contrast, is close. Europa is touchable in a way that no other potentially habitable environment outside Earth is touchable. We can send things there. We are sending things there. The cosmic loneliness of the universe is, for once, broken by the cosmic intimacy of a neighbor we can actually approach. And we have to decide, as a species, what we want to do with that intimacy. There is a darker thread here too, one that ties Europa to the larger question of why the universe seems so quiet. If habitable environments are everywhere, if buried oceans are common throughout the galaxy, then the question of where everyone is becomes sharper, not softer. The galaxy should be teeming. The radio sky should be crowded. The universe should be loud. But it is not. It is silent. And if Europa, after 4 billion years of perfect conditions, turns out to be empty, then that silence starts to mean something specific. It starts to suggest that beginning life at all might be the truly rare step, the great filter, the wall that almost nothing gets past. If Europa is alive, the silence becomes even stranger, because it means life is everywhere, and yet none of it has reached us, none of it has made itself known. Either way, the moon under our magnifying glass is telling us something about why we appear to be alone in such an apparently fertile cosmos. There is something almost tender about how Europa sits in this story. It has done nothing. It has not signaled to us. It has not invited us. It has not changed for our convenience or behaved in ways that suit our questions. It has simply existed, doing what it has done for billions of years, while we slowly figured out how to look. And in our looking, we have invested it with enormous weight. We have made it the test case for life beyond Earth. We have made it the proving ground for our most ambitious missions. We have placed on its small, icy shoulders some of the heaviest questions humanity has ever asked. The moon itself does not care. Europa would continue exactly as it is whether we noticed it or not. Our attention is entirely our own, and the meaning we extract from this little world will be a meaning we have made, not a meaning the moon has offered. That is the strange asymmetry of cosmic discovery. The objects we study are indifferent to us. We are the ones who are changed by the looking, and what we are being changed into is not entirely comfortable. We are becoming a species that knows there might be life next door, but has not confirmed it. A species that has the tools to ask, but not yet the tools to answer. A species sitting in the long pause between the question and the response, waiting for spacecraft that will not deliver their answers until the children of today are grown. We have to learn to hold uncertainty for decades. We have to learn to live alongside a question we may not get to see resolved. That is a strange psychological position for any culture. It demands a kind of patience that human civilization, especially in its current restless form, is not particularly good at. We will be tested by the wait. We will be tested by the answer, whatever it turns out to be. And in being tested, we will perhaps become something we have not been before, a species that has formally and seriously begun to look beyond itself, a species that has admitted, in the act of looking, that we may not be the only story being told in this universe. That admission alone is a kind of growing up. Whether the moon answers or not, the asking has already changed who we are. Come back one last time to that surface we stood on in the very first minutes of this journey. The ice that crunches like steel underfoot. Jupiter hanging huge and silent above you, banded and stormy, more than 20 times the size of any moon you have ever seen in a sky. The horizon close, the curve of this small world tighter than the curve of Earth. The cold so deep it would freeze your blood in seconds. And under your boots, beneath miles of fractured, irradiated ice, the dark sea, the oldest continuous body of liquid water in the entire solar system, the most patient ocean any of us will ever know. We have called this moon terrifying, and you might now understand why. It is not terrifying the way a monster is terrifying. It is terrifying the way a closed door in an empty house is terrifying. It is the dread of not knowing what is on the other side and being unable to look away. Europa is one of the most sealed environments in the solar system, and yet we are walking up to its door, slowly, deliberately, with spacecraft that took decades to build and decades more to arrive. We are knocking, and we do not know who or what is going to answer, or whether anyone is home at all. Both possibilities are terrible in different ways. A living Europa changes what humanity is forever, because it means we share the universe with strangers we cannot even fully imagine. A dead Europa changes us too, because it means a place this perfect, this old, this patient, can hold its breath for 4 billion years and never once light a single spark of life. There is no version of this story where we walk away unshaken. And yet, despite the dread, there is something almost holy about Europa in the older sense of that word. set apart, other, different from anything we have on Earth. A world where the rules of life we know may not apply, where time runs on a scale that dwarfs our species, where the conditions for biology have persisted longer than our own continents have existed in their current shape. There is a humility forced on us by this moon. Whatever we find, we will not find it on our terms. We will find it on Europa's terms, in a chemistry we did not write, in a darkness we did not choose, evolved across an interval of time that makes every human civilization, from the first painted cave to whatever the future holds, look like a single afternoon. To approach Europa is to approach something that does not need us. It existed before us, it will exist after us, and our brief flicker of curiosity will leave only the faintest mark on its surface. Maybe a few footprints. Maybe a few drill holes. Maybe a forgotten lander, half buried in fresh frost, quietly dying when its batteries finally fail. The moon will absorb our visits and continue. What we will take from Europa, on the other hand, will reshape us. Even if we never set foot there, even if every mission stays robotic, even if the answers come in fragments and across generations, the simple act of having reached for those answers will mark our species. We are no longer a species that wonders abstractly about life beyond Earth. We are a species that has identified a specific destination, built specific instruments, written specific names on specific spacecraft already in flight. We are a species that has, formally and publicly, sent out hands toward the dark. That gesture is not just a scientific gesture. It is a defining one. The reaching itself is the change. Whether or not we ever touch what we are reaching for, the fact that we are reaching tells us something about what kind of beings we are. There is also a strange comfort in the smallness of all this. The universe is unimaginably large. We are unimaginably small. The questions we ask are unimaginably old. None of us, individually, will live to see the deepest answers. None of us will walk on Europa. None of us will sail in its hidden ocean. Whatever happens there, when humanity finally finds out, will happen to people who are not yet born. They will read about us, the way we read about the early astronomers who first saw 4 points of light beside a bright planet on a winter night in 1610. They will know what we did not know. And that is okay. That is how it has always worked. Each generation hands the question forward, slightly more sharpened than they received it. We did not start this conversation, and we will not finish it. But we are in the middle of it, in a part of the middle that happens to be remarkable. The moment when Europa stopped being a dot and became a place. The moment when humanity started not just to wonder, but to go. If you have made it this far with me, through every layer of ice and every twist of the story, then you understand why this small moon matters so much. You understand why scientists who study it talk about it with a mixture of awe and unease. You understand why every new discovery, every new measurement, every new flyby lands like a small thunderclap in the planetary science community. Europa is not just another world. It is a question shaped like a world. And the way that question gets answered in the coming decades will be one of the defining stories of our century. So when you next look up at the night sky and find Jupiter, that bright, steady point of light that sits patiently above the trees, take a moment. Imagine, just to the side of it, too small for your eyes to see, that little frozen moon. Imagine, beneath its skin of ice, the dark sea you now know is there. Imagine the silence of that sea. Imagine the chemistry, the heat, the slow pulse of tides squeezing the rock at its floor. Imagine, just for a moment, that something is moving down there. Something old, something patient, something that has never seen the sun. And then come back gently to your own life, your own water, your own warm and noisy world. We have so much here, this small bright planet of ours, that it can be easy to forget how rare and strange it might be. Europa, by being what it is, helps us see Earth more clearly. It puts us in cosmic context. It reminds us that we are not the only ocean. We may not even be the most interesting one. If this journey moved you, if it left you with that strange mixture of wonder and unease that good cosmic questions always leave, please take a moment to like this video and subscribe to the channel. It really does help us continue to make explorations like this one. Drop a comment below and tell us what you think. Do you believe there is life in Europa's ocean, or do you suspect we are looking at the most habitable empty room in the solar system? Either answer is fascinating. Either answer changes everything. And either way, we will be there together, watching, waiting when the door finally opens. Until then, keep looking up. The universe is keeping its secrets, but it is also slowly starting to share them. And Europa is just the beginning.